What if I told you that in the early 1940s, during the darkest years of World War II, the Allies were fighting an air war they were quietly losing, not because of a lack of courage or firepower, but because their guns could not think fast enough? Watch to the end of this story and you will understand how that problem was finally solved and why the solution almost vanished from public memory. In the early 1940s, before the year 1942, as World War II raged across Europe and the Pacific, the sky had become the most dangerous battlefield on Earth. Air warfare was evolving faster than generals and engineers could fully comprehend. Bombers flew higher and faster than ever before. Dive bombers screamed down with terrifying accuracy. Torpedo planes skimmed the waves just above the sea. For soldiers and sailors on the ground, the aircraft overhead felt unstoppable. Around 1940, a group of soldiers stood on the deck of an Allied warship in the Atlantic, watching enemy aircraft approach at high speed. The anti-aircraft guns opened fire, sending bursts of black smoke into the sky. Shell after shell exploded harmlessly behind or beneath the planes. The gunners adjusted their aim, the guns roared again, still nothing. The enemy aircraft released their bombs and vanished into the clouds. The ship survived, but others nearby did not. Scenes like this were playing out across every theater of war. At the heart of the problem was a brutal reality that military planners had long tried to ignore. Shooting down a fast-moving aircraft with ground-based guns was almost impossible. An airplane traveling hundreds of miles per hour could cross the effective range of an anti-aircraft battery in seconds. By the time a shell reached the altitude where the plane had been, the aircraft was already gone. Before the United States joined the war, militaries relied on two main methods to detonate anti-aircraft shells. The first was the contact fuse. This required a direct hit. The shell had to physically strike the aircraft to explode. Against small, fast-moving targets, this was nearly hopeless. Even with thousands of rounds fired, a direct hit was rare. The second method was the time fuse. This was considered more advanced, but it carried its own deadly flaws. A time fuse was set before firing to explode the shell after a specific number of seconds. Gunners estimated how long the shell would take to reach the altitude of the enemy aircraft. If their timing was perfect, the shell would explode close enough to damage or destroy the plane. In theory, this sounded effective. In reality, it was a nightmare. Aircraft speed varied, wind conditions changed. Pilots maneuvered unpredictably. A shell set to explode 1 second too early or too late was completely useless. During intense air attacks, gunners often fired thousands of shells with timed fuses and achieved little more than spectacular fireworks. By late 1940 and early 1941, military analysts were deeply alarmed. Official reports from both the British Royal Navy and the United States Navy showed staggering inefficiency. In some cases, more than 10,000 anti-aircraft rounds were fired for a single confirmed kill. Ammunition stockpiles were being drained at an unsustainable rate. Ships and cities were paying the price. As America joined the war after December 1941, the problem became even more urgent. Japanese air attacks in the Pacific demonstrated terrifying precision. During battles like Pearl Harbor and later engagements around Guadalcanal, enemy aircraft penetrated defensive fire with ease. In Europe, German bombers and fighters challenged Allied air defenses daily. The existing anti-aircraft systems were simply not enough. Yet something strange began to happen in the middle of the war. Around 1943, Allied ships started reporting a sudden increase in aircraft kills. Battles that once ended with heavy losses now showed dramatically improved defensive success. Pilots reported seeing planes disintegrate in mid-air without a direct hit. Naval officers noticed that fewer shells were needed to bring down attacking aircraft. At first, no one spoke openly about why. Official reports were vague. After-action summaries used cautious language. The improvement was described as better training or improved fire control. But the truth was far more revolutionary. To understand how desperate the situation had been, it is important to grasp the physics of air defense. An aircraft does not need to be hit directly to be destroyed. A powerful explosion near the fuselage can shred wings, rupture fuel tanks, or incapacitate the pilot. The challenge was not firepower, it was timing and proximity. Traditional fuses could not solve this. A contact fuse required impossible accuracy. A time fuse required perfect prediction. What gunners truly needed was a shell that could decide for itself when it was close enough to kill. The idea seemed like science fiction. A shell fired from a gun experienced extreme acceleration. When it left the barrel, it endured forces tens of thousands of times stronger than gravity. Inside that shell, any delicate mechanism would be crushed instantly. Electronics of the era were bulky and fragile. Vacuum tubes shattered easily, batteries were unreliable. The very notion of placing intelligence inside a spinning artillery shell sounded absurd, and yet, across military research circles, the question would not go away. What if a shell could sense an aircraft nearby? What if it could explode automatically at the right moment? What if the gun did not need perfect aim or timing at all? In the early years of the war, this question was whispered rather than spoken aloud. Many scientists dismissed it as impossible. Others feared that even discussing such a concept would waste precious time. The war demanded immediate solutions, not theoretical dreams. But somewhere behind locked doors, the impossible idea was already taking shape. A secret effort was underway that would transform anti-aircraft warfare forever. The guns that were losing the war in the sky were about to become terrifyingly effective. And the answer to how this happened lies not in louder explosions or bigger guns, but in a tiny device hidden inside a shell, a device that could think faster than any human gunner ever could. In the late 1930s, as Europe moved steadily toward war, a quiet debate unfolded inside laboratories and military research offices across the world. It was a debate about possibility versus reality. The question was simple to ask and nearly impossible to answer. Could a weapon be built that detected an aircraft on its own and detonated at exactly the right moment? The concept was known in scientific circles as proximity detection. Instead of relying on contact or preset timing, the shell itself would sense when it was close enough to an aircraft to explode. If such a device could be made to work, it would solve the central problem of anti-aircraft warfare. Accuracy would no longer depend entirely on human calculation. The shell would finish the job. On paper, the idea was elegant. In practice, it appeared hopeless. Before the war, scientists in Britain, Germany, Japan, and the United States all explored variations of this concept. Some proposed optical sensors that reacted to changes in light. Others imagined acoustic systems that listened for engine noise. A few suggested magnetic detection. Every proposal ran into the same wall of reality. An artillery shell is one of the most hostile environments any machine can experience. When fired, it accelerates from 0 to hundreds of miles per hour in a fraction of a second. The force involved is immense. Any internal component must survive crushing pressure, violent vibration, and extreme heat. At the same time, the shell spins rapidly to maintain stability, creating additional stress. In the late 1930s, electronics were simply not designed for this. Vacuum tubes were fragile glass components. Even a minor shock could shatter them. Batteries leaked, corroded, and failed under stress. Circuits required space and careful insulation. Shrinking all of this into a device small enough to fit inside a shell seemed impossible. Military planners were skeptical. Official memoranda from multiple nations show that proximity sensing shells were often described as impractical fantasies. Some officers openly mocked the idea. Resources were limited, the war was coming. There was no time for experiments that might never succeed. Yet the problem refused to go away. As aircraft grew faster and more maneuverable, the inadequacy of traditional anti-aircraft guns became undeniable. Reports from the Spanish Civil War and early conflicts in China reinforced the same lesson. Aircraft could penetrate defenses with alarming ease. Timed fuses failed again and again. In Britain, early radar research inspired new thinking. Radar had proven that radio waves could detect distant objects. Some scientists wondered if a miniature radar could be placed inside a shell. The idea was daring to the point of recklessness. Radar equipment at the time filled entire rooms. Power requirements were enormous. Shrinking such a system into a few inches of metal seemed absurd. Germany explored similar concepts, but faced its own limitations. German engineers were highly skilled, but wartime priorities focused heavily on offensive weapons. Resources were directed toward aircraft, tanks, and rockets. Proximity fuses were studied, but never fully developed before the war ended. Japan faced even greater industrial constraints. While Japanese scientists understood the theory, manufacturing precision electronics at scale was beyond their capacity during wartime shortages. In the United States, the situation was different. Before America officially entered the war, its scientific community had already begun mobilizing. Universities, private laboratories, and government agencies quietly prepared for the possibility of conflict. Among them were physicists, engineers, and inventors who were willing to challenge conventional thinking. One of the most critical realizations came from understanding that proximity did not require intelligence in the human sense. The shell did not need to identify a plane. It only needed to detect a change in its environment that indicated closeness to metal. Radio waves offered a solution. If a shell emitted a radio signal and listened for reflections, it could detect when it was near an aircraft. The closer the aircraft, the stronger the reflected signal. When that signal reached a certain threshold, the shell could detonate. This idea still faced enormous obstacles. The electronics had to be small. They had to survive launch forces. They had to operate reliably in extreme conditions. They had to be cheap enough to mass produce. And they had to work without failure, because a shell that detonated too early or too late was worse than useless. Throughout 1939 and 1940, most experts believed these requirements were mutually exclusive. You could have reliability or miniaturization, but not both. You could have sensitivity or durability, but not both. The laws of physics seemed to say no, then war accelerated everything. As American involvement became inevitable, funding increased, research restrictions loosened. Scientists were encouraged to take risks that would have been unthinkable in peacetime. The urgency of survival changed the rules. Behind closed doors, a small group of researchers began experimenting with radical designs. They explored hardened vacuum tubes with reinforced structures. They tested new battery chemistries. They experimented with shock-resistant mounting systems. Failure was constant. Shells exploded on launch. Circuits failed under stress. Months of work vanished in an instant. Still, progress continued. What made this effort unique was not just scientific brilliance, but coordination. Physicists worked alongside artillery experts. Industrial engineers collaborated with academic researchers. The United States government quietly brought together talent from institutions like Johns Hopkins University and private companies with advanced manufacturing capabilities. This effort remained classified at the highest level. Only a handful of officers and scientists knew the full scope of the project. The fear was not just failure, but success. If the enemy learned that such a weapon existed, they might attempt to replicate it or develop countermeasures. By the early 1940s, the impossible idea was no longer dismissed outright. It was still dangerous, it was still experimental, but it was beginning to take physical form. Inside artillery shells tested at remote proving grounds, tiny electronic systems endured forces that should have destroyed them. Signals were transmitted and received. Detonations occurred at the correct moment, not by chance, but by design. The unsolvable problem was being solved, and as the war intensified across the oceans and continents, the United States was preparing to unleash a weapon that would fundamentally change the balance of air warfare, even as most of the world remained unaware it existed.
In the early 1940s, as America fully entered World War II, the pressure to turn theory into reality became overwhelming. The war no longer allowed patience. Every failed experiment meant more ships sunk, more cities bombed, and more lives lost. What had once been an academic challenge now carried the weight of national survival. Around 1941, the United States Navy and Army quietly committed themselves to solving the proximity fuse problem at any cost. The effort was placed under strict secrecy and organized through the National Defense Research Committee and later the Office of Scientific Research and Development. This was not a single laboratory project. It was a nationwide scientific mobilization. At the center of the work was the Applied Physics Laboratory at Johns Hopkins University. Physicists, engineers, and mathematicians were brought together with a singular mission: build a shell that could sense an aircraft and survive being fired from a gun. Many of these scientists had never worked on weapons before. Now, they were racing against time. The first obstacle was miniaturization. Electronic circuits had to be reduced to fit inside an artillery shell only a few inches wide. Every component had to be redesigned. Vacuum tubes were thickened, reinforced, and shortened. Filaments were re-engineered to withstand extreme shock. Glass envelopes were strengthened to survive acceleration forces that exceeded anything previously encountered in electronics. Next came the power supply. Ordinary batteries could not survive launch. They cracked, leaked, or failed instantly. Engineers developed a reserve battery that activated only after firing. This battery remained inert during storage and suddenly became active when subjected to the force of acceleration. It was a breakthrough that solved one of the most stubborn problems in the design. Then there was the issue of signal reliability. The shell had to transmit radio waves and receive reflections in a fraction of a second. It had to function while spinning rapidly through the air. Engineers solved this by designing antennas that used the shell body itself as part of the circuit. This eliminated fragile external components and improved durability. Testing was relentless. Thousands of shells were fired at proving grounds under controlled conditions. High-speed cameras recorded detonations, engineers recovered shell fragments and analyzed failures. Many early versions failed spectacularly. Some detonated inside the gun barrel. Others exploded immediately after launch. Each failure brought new data and incremental improvement. One of the greatest achievements of the American effort was mass production. A brilliant invention was useless if it could not be manufactured in enormous quantities. Private industry was brought into the program under strict secrecy. Companies like RCA, General Electric, and Crossley Corporation adapted their factories to produce proximity fuses at scale. This required unprecedented quality control. Every fuse had to function perfectly. A single defective unit could destroy a gun crew or waste a critical defensive shot. Assembly lines were redesigned. Workers were trained without being told what they were building. Many believed they were manufacturing ordinary radio components. By 1943, the results were undeniable. The proximity fuse was ready for combat, but even then its use was restricted. Military leaders feared that if a shell failed to explode and landed intact behind enemy lines, the secret could be exposed. As a result, initial deployment was limited to naval warfare, where unexploded shells would sink into the ocean. The first combat use occurred in the Pacific Theater. American ships facing relentless Japanese air attacks suddenly gained a powerful advantage. Anti-aircraft fire became devastatingly effective. Aircraft that once slipped through defenses now exploded in mid-air. Kamikaze attacks that might have overwhelmed ships were stopped before impact. Reports from naval commanders were astonished. Kill rates increased dramatically. Ammunition consumption dropped. Ships survived attacks that would have been catastrophic only months earlier. Sailors did not know why their guns worked better. They only knew that they did. The success could not be hidden forever. As the war in Europe intensified, the proximity fuse was finally authorized for use on land. It played a crucial role during the Battle of the Bulge in late 1944. American artillery used proximity-fused shells to devastating effect against German infantry and aircraft. Explosions above ground maximized shrapnel impact, breaking attacks and halting advances. German forces were stunned. Intelligence reports describe shells that seemed to explode at exactly the right height. Morale suffered, tactical plans failed. The weapon did not just destroy equipment, it shattered expectations. By the final years of the war, the proximity fuse had become one of the most important Allied technological advantages. It protected cities, ships, and soldiers. It saved countless lives. Yet its existence remained largely unknown to the public. The impossible idea had been made real through American scientific coordination, industrial power, and wartime urgency. A tiny device inside a shell had changed the air war forever. And yet, even as victory approached, the story of this achievement was about to fade into silence.
In late 1944 and early 1945, as World War II reached its final and most violent phase, the full impact of the new technology became impossible to ignore. In both the European and Pacific theaters, the balance of air defense had shifted. The skies that once belonged almost entirely to attacking aircraft had become lethal zones where survival was no longer guaranteed. Around late 1944, during the Battle of the Bulge, American forces faced a massive German counteroffensive. Weather grounded much of the Allied air power, leaving ground troops exposed. Artillery became the deciding factor. With proximity-fused shells, American guns delivered air bursts that detonated just above advancing infantry. The explosions showered shrapnel downward with devastating effect. German units described the fire as unnatural and unstoppable. Official U.S. Army after-action reports confirmed the results. Units equipped with proximity-fuse ammunition inflicted significantly higher casualties while expending fewer rounds. The technology did not merely improve effectiveness. It transformed battlefield doctrine. Artillery was no longer just a tool for bombardment. It became a precision instrument of area denial. In the Pacific, the impact was even more dramatic. Japanese air tactics relied heavily on speed, surprise, and sacrifice. Kamikaze attacks posed an existential threat to Allied fleets. Before the new fuse, ships often endured multiple aircraft penetrating defensive fire. After its introduction, Attacking planes were destroyed farther from their targets, naval losses declined. Fleet commanders openly credited improved anti-aircraft performance for survival in some of the war's most intense engagements. Yet despite its enormous influence, the proximity fuse remained shrouded in secrecy. Wartime censorship ensured that newspapers did not explain how Allied guns suddenly became more effective. Public credit went to bravery training or vague references to improved equipment. The truth was locked behind classified files. The secrecy continued after victory. In the immediate post-war years, geopolitical tension replaced wartime cooperation. The Cold War began to shape public narratives. New weapons like nuclear bombs, jet aircraft, and ballistic missiles captured attention. The proximity fuse seemed almost mundane by comparison, despite its proven impact. There were also disputes over credit. British scientists argued that early radar concepts inspired the breakthrough. American researchers emphasized the scale of U.S. industrial production and engineering solutions. Classified restrictions prevented open discussion. Many of the scientists involved returned to civilian life without recognition. Their work became a footnote rather than a headline. Declassified documents released decades later revealed the true scope of the achievement. Official histories from the U.S. Navy and Army acknowledged that the proximity fuse was among the most important technological contributions of the war. Some historians ranked it alongside radar and code-breaking in terms of lives saved. The irony is striking. A weapon designed to explode at precisely the right moment helped shorten the war and reduce casualties. Yet because it worked so quietly and effectively, it never captured the public imagination. There was no dramatic flash of a new aircraft, no towering rocket launch, no single defining photograph. Today, the proximity fuse is taught in military engineering courses and referenced in scholarly works on World War II technology. But outside those circles, it remains largely unknown. The secret weapon that changed the air war faded into obscurity not because it failed, but because it succeeded too well. The question posed at the beginning of this story now has its answer. The air war was not changed by bigger guns or braver gunners alone. It was changed by a tiny device hidden inside a shell, born from an impossible idea, realized through collaboration, and protected by silence.